Section 3.1, Systems of Equations in Two Variables. All right, so I'm going to run through this section fairly quickly. We're just going to get introduced into the idea of a system of linear equations. Sets of equations for which we seek a common solution are called systems of equations. We can solve systems of two equations and two variables by graphing. To do so, we look for where these equations cross or where they meet. So let's do this first example. Solve the systems graphically. All right, so let's graph each one of these sections. We have our equations. I like to number them just so I can refer back to them and you know which one I'm talking about. So for that first one, let's start off by solving for y. So I have y minus x equals 1. Let's move the x to the other side. So I have y equals x plus 1. For our second, we have y plus x equals 3. Let's solve for y. And we're left with y is equal to negative x plus 3. Okay, let's go ahead and graph. For our first one, I have a y-intercept of 1. And I have a slope of 1 over 1. So I start with 1, and then I go up 1 over 1, up 1 over 1, up 1 over 1. And that will help me create my line for my equation. For my second equation, I have a y-intercept of 3, and I have a negative slope, a slope of negative 1. So I have my y-intercept of positive 3, and then I go down 1 over 1. And our goal here when solving a system of linear equations is to see where they meet. And we see that they meet exactly at this point right here. That is our solution. That is our answer. So what is that point? That point is 1, 2. And that's pretty much it for this section. Now, the reason we start off with this section is because it visually shows us what we're looking for. What the downfall is about graphing is, well, for this one, we were lucky that it met up at such a pretty point. But what if they don't meet up at exactly a whole number? How do you round? How do you write that fraction? How do you write that decimal? It's really hard to tell. Let's do this next problem. So we're going to graph these two systems. We have our first one and our second one. Our first one is f of x equals negative 3x plus 5. And this one's set up for us already. Our y-intercept is 5. And our slope is negative 3. So let's go ahead and graph it. I find my y point at 5, and I go down 3 and over 1. And I graph my line. All right, next one. We have f of x equals negative 3x minus 2. So there we have a y-intercept of negative 2 and a slope of negative 3. So I go down 2, and then I go down 3 over 1. Okay, where do these lines meet? We have a problem, right? They don't meet at all. They don't cross. So if they don't cross and if they don't meet, there's no actual solution, right? And you could have actually caught this on later on, earlier on, not later on, because we see that our slope is the same. And recall that parallel lines have a same slope. Recall from our section, from our last chapter. All right, so we have to define some things for systems. Definition of consistent systems and inconsistent systems. If a system of an equation has at least one solution, then it's called consistent. If a system of equations has no solution, it's called inconsistent or an inconsistent system. I also see the word system being paired with this. All right, let's do this other problem. Okay, now we have to solve for y. We have to do some work, or you can do intercepts. Let's see. So we solve for y on our first equation. We have 3y minus 2x equals 6. I want to get y by itself, so let's move that x plus 2x on both sides. We're left with 3y equals 2x plus 6. Divide by 3, divide by 3. We're left with y equals, and remember that 3 divides both the numerator and denominator. So I have 2 over 3x, and 6 divided by 3, we get 2. So we have a y-intercept of 2 and a slope of 2 over 3. Our next equation, we have negative 12y plus 8x equals negative 24. Let's solve for y. Let's subtract 8 to both sides. 8x minus 8x, that's 0. We're left with negative 12y equals negative 8x minus 24. Divide by negative 12 to get y by itself. So I'm left with y equals, that 12 divides each one. So we have negative, or 8 over 12, and the negative divided by negative is positive, and 24 divided by 12 gives us 2. And we need to simplify that fraction so that I have y equals, they can both be divided by 4, 2 over 3x plus 2. So here are our two equations. Do you notice something funny? They're the exact same equation, right? So I go up, I find my y-intercept at 2, then I go up 2 over 3. And that's my first equation. And for my second equation, I have a y-intercept of 2. I go up 2 over 3 for my slope. And that's my second equation. They are the exact same equation, so they overlap, touching at every single point. Another type of equation we can have is a dependent equation and an independent equation. For a system of two equations and two variables, the graphs of the equations are the same line, the equation is dependent. And if the graphs of the equations are different lines, then the equations are independent. So for that first equation, this example where we had the lines overlapping, it's still considered consistent because it says at least one solution. So that's considered consistent and dependent. And here are pictures to help us consider all of our options. So this is graphing to solve your system, and the idea is to see where these lines cross. Now, in our path to looking for where they cross, they can have one solution. They can have no solution, that means the equations are parallel, or both equations are actually the same equation, thus creating one line that overlaps. On the first one, if we have one solution, we say the graphs intersect, the system is consistent, and the equations are independent. In our second option, if they never cross, the graphs are parallel, the system is inconsistent, and the equations are independent. And for our third option, equations have the same graph, the system is consistent, and the equations are dependent. All right, that was section 3.1, Systems of Equations in Two Variables. Thanks.